Hi, welcome to another lecture on Calculus 3. Today we are going to start a new chapter, functions of several variables. Let's go ahead and start this topic. So, functions of several variables are as common as the functions you had seen in Calculus 1. A very simple example would be the function that expresses the area of a rectangle in terms of the length of its sides. So suppose we have a rectangle. We call this side, say, x. This side we call it y. Well, the area of this, obviously, x times y. So this is a function of two variables, x and y. We call them independent variables because you can independently choose x and y as whatever you wish, well, positive numbers, but whatever you wish, and then you get the area depending on the choice of these two. So x and y, these are going to be referred to as independent variables. Then a, which is calculated through this, is going to be referred to as a dependent variable. Simply meaning the value of a is going to depend on what choices you have on x and y. Notice the difference between here and what you had in Calculus 1 or pre-calculus. In those settings, one of these two depended on the other one. Either y is given in terms of x or x was given in terms of y. But here at the get-go, x and y have their own mind and you can choose them whatever you want. Very simple, similar example is the volume of a box. Well, volume of a box depends on three variables, x, y, and z. You can choose these independently from each other. So if I have a box, and let me draw the back walls or lines with dotted lines. So let's suppose this is the dimension x, say this is dimension y, and this is the dimension z. Volume is the product of these three, and that is a function of three independent variables. Something a bit more perhaps complicated than this would be the surface area of this box. What's the total area of this box? Let's show that by S, the surface area of the box. So on this side, for example, you see this, let me mark this. This is a rectangle whose area is x times z, and then there's another rectangle back here identical to the one on the front, that's also x times z. And then on this side you have another rectangle. This is y times z, the area is y times z, and the one on the top or bottom, this is going to be x times y. So the total area of this becomes 2 times, say, xy plus yz plus zx. So this is the surface area of a box. And that is, of course, the volume of a box. And that was the area of a rectangle. So the idea was that these quantities that we have here, x and y and z, they are all independent of each other. Sometimes we go after applications, not just simple geometry. For example, you can have interest. Let's look at the simple interest. It is a function of principal, how much money you put down, interest rate, and time. So this would be a simple interest. You see, for example, in your pre-calculus classes sometimes. Sometimes you see the total on account inclusive of interest and the original principal with formulas like this: p times exponential of rt, and this would be under the topic of compound interest. So in these cases also P or T are going to be considered your independent variable. S is going to be dependent variable. E is just your famous number, Euler number 2.71821, etc. And you're putting P dollars down at the rate of R for time T, compounded continuously, and the total amount is supposed to be S that you see here. So all of these things fall under one notation that we are going to have. So let's make up a notation for this approach. The notation, well, we have to have a list of variables for our independent variable. Typically from the end of alphabet we choose them in order, put them in a parentheses. By now I have a so-called ordered pair. Ordered pair means you're not allowed to change their order. Things could be different. Of course, principle is different from time. You cannot mix them up and such. Then you have the name of your function. So the name of function is abbreviated to a single letter in mathematics. Typically engineering uses a lot more letters than that. But, well, you have to specify what is it that you have in your mind. The name of your function is going to be called f. So f could represent any one of these things. Could have been volume, could have been surface area when you have three variables, and so on. And then you have an output. Output is the dependent variable here. So this is typically the next letter of this bunch, or something clear as to how we are specifying the output. So ordered pair, this official name for this thing is independent variables. And then this one is called the dependent variables. Sometimes, to use a terminology that is closer to what engineers might use, I might refer to this thing as the input to a system, and this one as the output. That's a little bit easier to pronounce than this mouthful of independent variables. Well, sometimes you have some restrictions as to what numbers to use, and then some other restrictions as to what numbers are going to come out. So we have always a concept of domain of your function. So if your function is called f, we talk about domain of f, and that's a set of numbers that you're allowed to use in your function. Typical math functions have some sort of restrictions. On engineering they even have more restrictions. So domain of f would be a description of set of x and y values which you are allowed to use. So for the domain of a function could be a certain region in the xy plane where you are allowed to use those. Typically dotted lines refers to something you're not allowed to use. And then out comes something that's called the range of f. Range of f will be a description of what kind of a number is going to come out. So the z is also going to be reflected on some axis. So let me just draw some arbitrary line here. Let's call that the z-axis, and it could be that you are only going to end up with a certain set of numbers on this axis, and we are going to call that the range of the function. Let's go ahead and specify this thing a little bit more clearly with an example, a simple example. Suppose I consider the function z. Let's give it a name, f of x and y, and then specify what that function is by some formula. Here's a formula: x squared plus y squared, say minus 1 in a denominator of this fraction. So this is some function. Perhaps not as meaningful as what we had here, but it's just the same idea. You have some input variables, some output variable, and a description of how to go from input to the output. That is a description of a function. Now, question might be, well, how would you describe this function? Writing formula is one thing, understanding it is something else. well, simplest thing we could start with is what is the domain of this function. So one good thing to ask is what's the domain of f. Well, what was the issue of domain? From way back in algebra, starting middle school, you are instructed on certain operations have certain restrictions on them. So most famous of all of these things, of course, if you have a fraction, so if I have a fraction which has say 1 on the numerator and some expression on the denominator, what is the domain of that expression? Well, the domain of this expression is that any value in the denominator other than 0 is acceptable. So here I have a so-called expression, something we write with some variables in it, and then there are restrictions on what you can use in this. So I'm using the letter E to indicate some general thing that could be in the denominator itself is some expression. So here is a restriction on what you're using here. So of course when you're dividing, you don't want to have 0 in the denominator. So that is the main thing that we have to watch out for here. Some other problem, you might come across a square root. Well, if you have a square root, of course you want the expression in the square root, the so-called radicand, to be non-negative. So we have a restriction like this. Applies to square root, fourth root, and all the even roots. So let me write 2n here for all sort of roots. What else do we have of this type? Well, logarithm also comes with a restriction. The input of the logarithm has to be positive. What else? How about items in trigonometry? Well, when you write something like tangent of an angle, what kind of angles are you supposed to use? Well, I cannot use like pi over 2 and such angles here, so that is ruled out. So E has to be different from pi over 2. Of course, 3 pi over 2 minus pi over 2 minus 3 pi over 2, any odd multiple of pi over 2 is out of consideration. So tangent is, of course, sine over cosine. The cosine in the denominator is causing this restriction. Same way with secant. Secant of an angle suffers from the same sort of restriction. How about cotangent? Cotangent of an angle, that should not be, well, cotangent of 0 is infinity, cotangent of pi is infinity. So any multiple of pi, so let's write n is for any whole number, that is ruled out. And in same fashion, cosecant of an angle has the same restriction. Okay, so for the items that you see from high school onward, these are the basic restrictions that you have. Of course, if you study more advanced functions, you'll have more restriction. Many functions have some sort of a restriction on them, and here we are listing a few of these cases that you see most often. So most of the problems you see is either a fraction like this, you have to watch out for the denominator, or square root, and then that has to be non-negative, occasionally a logarithm as well. Okay, let's go back here. So domain of f is therefore all set x and y such that the denominator stays away from 0. Let's write it a little bit more understandable. X squared plus y squared has to stay away from 1. Well, what is x squared plus y squared equal to 1? X squared plus y squared equal to 1, that is a circle. It's a unit circle. So what we are saying here, you don't stand on the unit circle. Either be out of it or inside of it, but right on it, the denominator becomes 0, and the function is going to misbehave meaning what here is that it's going to go to infinity. If you divide a number by a 0, you get infinity. Let's go do a quick look at this thing, see what okay, so let we open this very useful application that we have here. X squared plus y squared excuse me, plus y squared minus 1, that's the item in the denominator. What if I graph this thing? So I just press return. You see something is odd happening. You see, let me turn this thing around. It has two pieces to it. What happened? On that circle, you kind of see it from here, or let's see it from here. On that circle, the function jumps to infinity. In fact, goes from plus infinity to minus infinity, and that creates a rupture in the surface and splitting of your graph. And of course, that is not something you want to see in any kind of an application you have in mind, because there's a wild jump in the value of the function. Typically it means something is going to go wrong. So the point at which this rupture happens is considered to be out of the domain of the function, and that is what we are trying to get at here. That is when this denominator is going to become 0. So here let's try to practice a little bit drawing this thing by hand ourselves and trying to get a sense for what is going on. So here's my x, y, z axis. So on the xy plane, I'm going to identify x squared plus y squared equal to 1. That is the set of points where something problematic is happening. That's where you're dividing by 0, and therefore you're excluding it from the set of points where you are doing legitimate operations. So the domain, if this red line is not acceptable, if it's outside of a domain, it means you have to be either inside or outside of the circle. So another way of expressing this thing is the domain is equal to the region inside or outside of unit circle, that red thing. So if I'm inside, for example, when x and y both of them are 0, I am inside. My fraction becomes minus 1. I am down here at some negative value. Let's write that in blue. If x and y come close to the edge, then this denominator comes close to 1, and I divide by a small negative number, and as a result my surface is going to go down like this. That's what you saw over there looking like a bullet here. So that is the surface that is on this side. So if I'm inside this circle, then I'm down here. If I'm outside of the circle, for example, here I'm at point 2 and say x is 0, y is 2, so this becomes 1/3. If I come close to the circle again from outside, I'm dividing by a number that's positive and close to 0, so as a result I'm going to go up toward infinity. If I go way out, away from the circle, well, the denominator is going to become very big, and then I'm going to approach 0. So the surface I see here is the surface of revolution of this figure that kind of looks like this. It's like imagining a kind of a volcano that is here. The mountain range has an infinite tail, and here as you go higher and higher, you approach a cylinder that is built on top of this red circle. So instead of the asymptotes that you had in calculus 1, we have a kind of a wall, a cylindrical wall if you wish. So consider a kind of a cylinder, like I draw it in the same red color here. So the surface up here is going to approach this cylinder from outside, and down here is going to approach the cylinder from inside. So that is what is expected from you to be able to do this thing in your mind, to kind of capture the essence of this surface as to what is happening near its asymptotes, and have an idea as to the reason for that. So let's go ahead and continue and draw a few more of these things. So suppose I ask you, consider z is equal to the logarithm of x times y, x times y. The question is, what's the domain of this function? So let me go ahead and name it something, so we refer to it by its name. So suppose I say, call this z is equal to, since it was a logarithm, call it L of x and y, and there's a logarithm of x times y. Okay, you can give any name here you want. So the question is, what is domain of L? Well, domain comes from the restriction of the logarithm. Well, what was the logarithm? Remember? Do you remember? Let me ask you, what can, before you look at that picture, what was the restriction on logarithm? What kind of numbers are there that you cannot use in a logarithm? Do you remember? So it was a set of numbers that are negative are not allowed. 0 is not allowed either. Only positive numbers are allowed for the logarithm. So for logarithm, you have to stay positive. So what does that mean? Well, the input of my logarithm is x times y. It has to be positive. X times y. I want this to be positive. Well, what section of the coordinate plane corresponds to solution of this inequality? You should be able to answer that quickly. What section of this is the solution of that inequality? What is that? Okay, so if you said, what did you say? If you said the first and the third quadrant, here x times y is positive, here both x and y are negative, therefore their product is positive. xy here is positive, xy here is also positive, and these two other places, of course, they are negative. And on the axis, what's xy on the axis? Can you tell me quickly? Well, of course, xy on the axis is 0. That's where we are crossing. So what's the domain? Logarithm only accepts positive, therefore the domain is inside the interior of first and third quadrants. Okay, when you say interior, means you cannot be on the lines either. How would you specify that? Well, either x0 and y equal to 0 both, or x is negative and also y is negative. So these are the two regions, the region 1 and region, let's call this thing region 2 here. So this is region 1, let me write without the parentheses, and region 2 is of course you call that quadrant 1, and this one is called quadrant 3. So if you want to call them by quadrant name, this is quadrant 1, and traditionally this is referred to as quadrant 3. So You can call them in region 1, region 2, however you want. So either way is fine. So let me go ahead and just make it just one name, quadrant 1. Let's call this thing quadrant 3 so that we don't create a different order and create some confusion for some students. Quadrant 1 and quadrant 3. That's fine. Okay, so we have the concept of domain. We have that's going to help us to become accustomed to 3D pictures and think in that sense. Next idea is some basic functions. What kind of functions do you start with in high school? Well, you have like x and x squared and x cubed and so on, and then you have x plus x squared and so on. You call them polynomials. Here we have polynomials as well. Polynomials are going to be more complicated now. Let's consider a polynomial with just two variables, x and y. Well, here's a polynomial. You are only allowed to use whole positive powers and the products. And so on. And you can have a constant, of course. So this one is called the quadratic polynomial because the highest total power I see is 2. And this one, 1 and 1 adds up to 2, so total power of this thing is just 1. Then we have rational functions. Rational functions, let's use the letter R. So that would be ratio of two polynomials. So if I have one polynomial, typically polynomials referred by P and Q and such, and then another polynomial, and I take a ratio of them, well, I have a rational polynomial. Then I can have, of course, functions that are built on roots. So I can, or radical polynomial, radical functions. So if I have a radical in my description of the function, I have an example of radical function. So suppose we go ahead and take a look at one of these things. Suppose we say graph z is equal to for example 25 minus 4x squared, say minus 9y squared. So now we are looking at something that might look a bit complicated at the first inspection. So what is this? Well, it's some polynomial under square root, and therefore it's a kind of a root function. What kind of steps am I going to take to graph this thing? Well, what do you think we should do first? One of the very first thing we said we need to do to inspect a function is its domain. And how do we go after the domain of this? What should I do to figure out the domain of this function? So let me also give this one a name, z. Let's call this thing, say, h of x and y. And then a question, first question is, what's the domain of h? What do you think I should do first? He said, with square root, you need to have what? Square root, the radicand has to be non-negative. So I need 25 minus 4x squared minus 9y squared to be larger than or equal to 0. To rearrange this and write it in a way that's a little bit more pleasing, so perhaps we take the x and y on one side and 25 on the other side. Notice this is the same as that. Well, now comes a litmus test. How well do you remember your calculus 1 or pre-calculus? Why do we need that? I need to quickly say, what is the boundary of this shape? That is, I want this quantity to be less than or equal to 25. To figure out where the dividing line is, I go after the curve that is described by 9 squared plus y squared equals 25. That's going to decide where I'm going to be less and where I'm going to be more, and it's going to give me the boundary between two regions. One is inside the domain, the other one isn't. Well, can you quickly tell what the graph of this thing is? So what we need here is a very good background from pre-calculus to tell the graphs of various basic functions, to be able to figure out graphs of these things in 3D. Okay, so what is this one? This is an ellipse. If you remember, to get that ellipse, to write it in a standard format, I divide by 25. So x squared over 25, 9y squared over 25 is equal to 1. Make it more standard, I bring the numerator into the denominator and write it as, this is 25 fourth, which is 5 half squared, and then this is y squared over 25 ninth, which is 5 third squared, is equal to 1. If you remember, these are called semi-major and semi-minor axis of your ellipse. So if you have your xy coordinates and then you draw a box, 5 halves this direction, 5 third in this direction. So let's draw a box. Hopefully you draw your box nicer than I drew it. The ellipse is tightly inside this box. Of course, many wonderful properties of ellipse. We're just skipping so much. Remember, there are two focal points here that have many wonderful properties there. You study that in pre-calculus, but that's gonna get a main track for this problem. So what is it that we want from this graph? We say our domain is set of x and y's that are less than this quantity. So where do you think I should be? Inside of this for 4x squared plus 9y squared to be less than 25, or should I be outside? Easy way to check is just pick a specific point and see if you are on the right side or not. So for example, if I put x and y equal to 0, that 0 is of course less than 25. So inside of this ellipse matches exactly where I want to be, and therefore interior of this ellipse is where the domain is. So the domain of this thing is this. What happens right on the edge? Well, right on the edge you have, so this is the domain, this is the domain, and right on the edge it becomes equal, and inside of your radical is 0. Square root of 0 is well defined, still 0, no problem there. And that is the domain. To see this thing a little bit clearly, let's go ahead and take a look at our trusty software here, and let's write one that it accepts square root or not. Square root of what was it that we had? I already forgot. 25 minus 4x squared. So I'm going to write 25 minus 4x squared minus 9y squared. Okay, this is restricting it inside of that box, but let's see if we can expand it a bit more. Okay, now I have more room down here. So you see this is built on top of that ellipse there. The top of this thing is still chopped off. We have to go inside the software and expand our view to see. So you see inside of this ellipse I have a description for my function, but on the exterior of this ellipse out here there is no ceiling or the floor above or below us. That means the function doesn't exist in those areas. Okay, so that was one example of how to analyze this function in terms of the domain. And then once we get the domain straightened out, then we have to work still pretty hard to get a graph of a function. You remember graphing in calculus was pretty hard. Now when you go to 3D, it's just that much harder. We are just looking at some simple examples here. So we had that base, and as you go toward the center, so I had z is equal to, what did I have? Z was equal to 25. So let's take an easy point, like at x and y equal to 0. If I put them equal to 0, my z becomes square root of 25, which is 5. So 5 is going to be way up here. That's why getting out of our picture over there. And then inside, if I pick x and y's, I get a sense as to how this thing is approaching its zenith. So some sort of a graph looking like a bump on top of the page, looking something like this. So that is how to go about quicking this, sketching it in your mind quickly and getting some handle as to what is going on with respect to. Okay, one of the ways that we try to handle these kind of complicated cases and graph and describe a graph is through so-called contour levels, or sometimes they are called the level curves. This concept is so standard. You see it on the evening news pretty much every day when they talk about the weather. The weatherman likes this concept more than anybody else in the world, because they are always showing you the temperature, where is the dividing line between areas where the high is going to be, say, 90 versus the ones where the high is going to be 80 and such. So those graphs you see on television pretty much every day in the news, there are a bunch of contour lines. What's the idea of a contour line? So typically you have some function f of x and y. You want to describe it. Could be a complicated function. Let's go ahead, start with something simple. So we here I have my x, y, z, and suppose we have just some nice curve here. Okay, to describe this surface, what we do is that we slice it up. We slice it up with the planes that are parallel to this base plane here. So we consider a bunch of planes parallel to the xy plane and cut up our surface with that. So I might cut this thing up here. I'll get a curve like this. If I cut it right all the way up here, I just get a point. If I try to cut it up higher, well, I don't get any cut at all. Instead, I come down here, I get here some other cut. I cut this thing and then another cut and so on. If you take all these cuts and drop them on the xy plane, you get a picture like this. So you can look at the contour levels on the surface, or you can drop them all on the surface on the XY plane and look at them down there. These are referred to as contour levels or level curves. They are, as we said, they use them all over the place for all sorts of applications. So all sorts of names are used instead of calling them contour levels or level curves. You don't see your weatherman using those words. Sometimes they refer to words such as isobars. Isobars means your pressure is the same. So these are areas. So let's write the locations where or let's say locations with same pressure. So if they on the map they draw a line and says this is an isobar, means all along that line the pressure is some same number. Sometimes you are going to look at so-called iso-therms. It means the temperature is the same. So you're going to see a lot of these things in your thermodynamics. In electricity and magnetism, similar concepts used. They call it over there, equi-potential. It means the potential energy is the same. Of course, the people in geology and land surveying use that all the time, and then they get a topographic map of an area. So we have topographic cut or topographic maps of something, and that indicates where the heights of the places that you are drawing there are all the same. So similar concepts used all over the place. Let me go ahead and show this thing in that software, see how to do it over here. Let me leave this thing here and pick another one. I was going to talk about that too, but maybe let me leave this thing here, go back here and erase this one. So let's just pick somebody from here, just the basic graph, it always shows up. Or let's just get something less complicated. Let me just drop the exponential and just have it as a get something that's better behaved. Okay, that's what I was looking for. Okay, let's take this thing. This is like the default picture here. It's kind of smooth and nice, and then wouldn't give us any headaches. So this is 7xy over exponential of x squared plus y squared. Okay, this thing gives you your contour plot. You see it says draw contour plot. Okay, you still have to draw it, so you make some specification here. C are the heights at which you want to make your cut, so you decide on that, and then you choose your color, and then it's okay, draw me the contour plot. So okay, here's a contour plot of it. Now all of a sudden you say, well, what happened to my surface? So here you have to take some additional steps to see them together. So I go ahead and then add another one of these. So add another function to this, and then I make sure it's the same function. So it was this one, is that right? Okay, so take a function, draw its contour plot with this, and draw the function a second time. now the magic happens. You turn this thing around. You see how great that is? That is the contour plot of that surface we were having. You see those red lines? We are cutting that surface parallel to the XY and creating slices like that. If you take these curves and drop them on the XY, you get this. So this is one interpretation of what the contour plot is. If you want to have them on the surface itself and look it up there raised in 3 dimension, well, that is what you see it here. That is your contour plot. So you are going to see a lot of these things in a huge number of engineering applications. You want to get good at interpreting the pictures and so on. So these are contour levels. You see 0.2, 0.4, it kind of gets crowded here, 0.6, 0.8, 1, and so on. When you see the lines very close to each other, it means the values are changing rapidly. If you see big spacing between the lines, it means that the changes are gradual and it's not as steep. So this is the side of the mountain that's not so steep, and this is the side of the mountain that is quite steep, and so on. So pretty much any engineering software has something for this, and you go ahead and choose your level curves and use the resulting picture for your work. Okay, so we got out of chapter 12, which was getting pretty heavy at the end, and thankfully chapter 13 starts rather nice and easy. So we are taking a little bit of breather from all those heavy formulas and such, and just looking at very nice pictures, simple problems. But remember, you need to know graphing from calculus and pre-calculus. You need to know the concept of domains and things of that sort, and the problems in this section will be quite simple. Okay, until the next meeting, good luck and God bless.